Hi, thank you for signing up this research experiment. In this video, I will explain you what this project is about, what we ask you to do, and what we are gonna measure on you during the experiment. For validity and equality between each participant, this video will be the only explanation you will get. So please give extra attention. You can watch it as many times as you want, and you can even re-watch it during the experimental process. So if you're ready, let's get started. Currently, there are several research on automation and robotics all around the world to make robots more useful in various tasks. While robots are durable, repeatable, accurate, no need food, no need sleep, but humans are still better and excellent in problem solving and decision making. So instead of using either of them completely in the tasks in industry or in various applications, we might think about making a human-robot team and use their better sides whenever it is needed. So this project is basically aiming for that. So the purpose of this project is to investigate learnability, feasibility, efficiency, intuitiveness, applicability of such human-robot teams in a sample cooperative lifting scenario. So the theory is that humans and robots can be an efficient team with enough training. It's like learning how to drive. You need to take a driving license. For that, you need to have enough training. Otherwise, the car can be a killing machine. Additionally, different from the majority of other related research going on in the world right now, we are not using cameras. So the robot does not have eyes in our application, but we are using something else to give information for that. Although camera-based systems are quite precise and accurate, they are not very reliable for human-robot applications, particularly for industrial settings. What I mean for that? If you have a camera system, it is not as portable as the system we are using now, and it requires lots of calibration time, and also it is very prone to occlusion, losing line of sight, color changes, lighting changes, etc. Therefore, we are using inertial measurement units. This is an inertial measurement unit. It has an accelerometer, gyroscope, and magnetometer inside. First, you will be equipped with 5 sensors, as you see. We are able to measure the velocity, the acceleration of your arm or your chest or wherever we attach this, and also the magnetization around that tiny object. Therefore, we are able to calculate the orientation of this thing, and also using that orientation, we are able to calculate your joint angles. And using the joint angles and your arm, your body, as we call the biomechanical model of human, we are able to capture your motions. There is also an armband which contains several EMG sensors, and those are measuring your muscle activity on your arm. We are using it to control the gripper. You are going to carry this table from that place to this place. Your aim is to complete the task as smooth and as quick as possible. However, it is more important to accomplish the task than doing it fast, so you just need to learn. First, you will be equipped with 5 sensors. Afterwards, I will calibrate your posture. As you see, that is what we call an pose. To be stable in the step, not to bend, is important. If the calibration is not good, you might experience some difficulties in controlling the robot. You will be seeing each step what I am doing on the app screen. When things are ready, I will ask you to go initial pose, which is the one you see on the screen right now. 2 hands lifted from elbows and palms are looking down. This is a suggested initial pose. However, if you think that you will have a better control with slightly different posture, that is also up to you. You are very welcome to adjust a little bit, maybe the distance between your hands, maybe the L shape, how perfect L it is, maybe a little bit higher, maybe a little bit lower. You have some sort of freedom in that posture. technical alert, you just need to remember that this is the origin of motions. So your motions and robot motions will be mapped exactly from that point. When I give you the sign of now the robot is in your hands, you can start controlling the robot. Now let's talk about 4 different states of how you control the robot. Also, how will robot control you? 4 different states of this experiment are idle, approach, co-lift, and release. In the first 2 states, you will be the leader in idle and in approach. In the co-lift state, you will share the leadership with the robot. And in the release state, the robot will be the leader. You should be somewhere close to the table as you wish, and you should be able to move your arms freely. 2 of your hands are lifted horizontally. You can still move freely in this state, but that is very, very important. Your right palm looking downwards, because the transition state is triggered when you rotate your right palm upwards. Then the robot will start moving. If you move your right palm up or your wrist looking upwards, even accidentally, the robot will start moving. So, when you feel comfortable, you can rotate your right palm upwards to transit the approach state. The robot will immediately be activated and start moving. The combination of both your right and left hand will create a motion command for the robot. What I mean with that, if you lift your both arms upwards, the robot will move upwards. If you move both of your arms downwards, the robot will move downwards. But if you move one upwards and the other one is downwards, depending on how much up and down, the robot can stay stable or move to the direction of the hand that makes the biggest motion. So we are calculating as a combination of 2 hands. This state might need some practice before you trigger the next state. So take your time and try to understand what kind of motions of you makes what kind of motions on the robot. Particularly in the first couple trials you will have, I would suggest you to investigate your intuitiveness on that a little bit more. When you feel comfortable in controlling the robot in this state, then you can grab the table and then clench your right fist. The robot will start immediately moving upwards, so to say, helping you to lift the table slowly. In this state, you are no longer the leader. The robot is the leader of carrying action, and you are still some sort of leader in deciding the direction. So this state is we call shared control. Initially, the robot will start lifting the table until you state the robot to do something else. How do you do that? Your hands are full, right? So we cannot use our hands to control the robot at the moment. We need to just show the robot with our elbows where we want to go with the table. To tell the desired direction, you need to give a gentle push to the robot, as if you poke your friend to look at you. Then the robot will stop. Then you can adjust your elbows to left, right, or upwards, as you see also on the screen. And with your next push, the robot will start moving to that state. Additionally, you can move downwards, but for that, instead of poking your friend, you need to pull her or his hair. So you need to pull the table. And the visual screen is your best friend at this stage, particularly in first trials. So hopefully you will remember looking at the screen to adjust your elbow heights. And also you will see some asterisks around the elbow directions. That is also reflecting the amount of force you are applying to the robot, both push and pull. When it is white and a bit blurry, then it is still under the threshold. When it is green, then you pass the threshold and the robot will start moving to that direction. How does this elbow height thingy work, there will be a threshold in the beginning we set together. If your left elbow is higher than that threshold and right elbow is lower than that threshold, then the robot will move left with your poke. Also, if your right arm is higher than threshold and the left arm is lower than threshold, then the robot will move right with your poke. If both arms are higher than the threshold, then the robot will up when you poke. And for downwards, you need to have both elbows lower than the threshold height, and you need to pull the robot. During the cold state, you will carry the table in 2 different places. And those places are physically available for you as wooden buttons, as you see on the screen. So you will first press or push the first button, and then you will move to the second one. Meanwhile, I will clean up the first button from your path, and then when you are done with those 2 buttons, you can trigger the release state. When you are done with 2 buttons, you can gently release your right elbow to downwards. As soon as you do that, the robot will take over the full leadership, and then you will be the only follower now. You are no longer able to control the robot, you just need to follow the robot to a predefined state. Summary. You are asked to do those 4 states in total 10 times. I will be observing both of your motions and robot's motions during the whole experimental process. Before I give you the stage, I would like to give a few warnings. First, orientation translation. This challenge requires a little bit technical explanation, so I hope you can bear with me. By definition, rotation is an action of rotating about an axis or a center. Translation is the process of moving from one place to another place. Human joints have both of those properties. Mostly it is rotational. It has translation when you are moving yourself. But the translational feature of the joints we are using on our upper body is very limited. Therefore, in this experiment, we neglected the translational motion of our joints. However, the shoulder joint has some translation, particularly in big motions. So if you are doing big motions on your shoulders, then there will be some sort of deviation between your actual posture and the simulated version of you. And this means 2 things. First, if you walk, the simulation will not walk. The freedom you have is from your upper chest. Either you can stuck at point and try to control the robot from one point, which is your origin, or if you want to or need to walk, you can still do that, but just keep in mind that the robot will not register it, and when you move right, the robot will not move right. If you want the robot to move right, you need to give more distance from your chest to wrist. Second, since the translational motion and the soft tissue artifact is neglected in this setup, everything is based on the orientational calculation. So sometimes you think that you're moving just purely right or just purely left, but it is actually not registered completely. So you need to double check between what you think you are doing and the simulated version of you, so that you have a pure linear motion if that's what you want. You will get used to controlling the robot, even not looking at the screen at some point, probably at the end of your 10 trials. But in the beginning, it is quite important, because we humans think that we are doing something with our body, but actually when we focus on something, we are slightly distorted than what we think we are. Just imagine how much humpback you get when you're sitting on your desk and working on the PC, because you're so focused on your PC and you can't consider your posture. Also, think about ballerinas, how many mirrors they have in their studio to make sure that they are doing the posture as they think they are. This is like the mirror in the ballerina rooms for the robotics settings. This screen shows you how the system sees you. and you have some freedom how to control the robot, so please investigate. Second challenge is a workspace challenge. This also requires slightly technical explanation. The robot cannot reach the corner of that room, right? So it has the limitation. So do you. You have, even though you are able to walk, as we mentioned, it's not registered in the system. So you have a workspace, which is the limited reachable area, both for you and robot. And these workspace sizes are not equal. Sometimes the robot might reach its workspace limit, but you still have some freedom, or vice versa. If he goes so much on its limit, the robot will go protective stop. This is an inaccessible position for the robot. So try to be in the center of the workspaces, both for you and robot all the time, for the smoothness of the application. And about the workspaces, maybe it is important to highlight there. If you are in your limits of your workspace, you can stop at any time and position yourself in somewhere comfortable, and then you can rotate your hand and continue the motion from that point. The robot you are going to work with is a type of collaborative robot, which is also identified as human-friendly robot. This friendly robot achieves that by constantly measuring the force on all joints and also the end effector, or where its hand is located. When you are carrying a table, actually you are loading a little bit force. When you are pushing and pulling the robot in co-lift state, if it is too much, you may risk the robot to stop. When you are trying to grasp the table, if the robot's upper finger is too close to the table, then the robot actually pushes downwards. It will go into a protective stop. The end. Now it is the experiment time. I hope this video was useful. You can rewatch it at any time you want. Good luck.